Well, thank you very much for the introduction, Alan. I'm Brian Denton. I'm from University of Michigan, and my co-presenter, Jonathan Woodall, and I are going to tell you about a project that we did with Duke Cancer Institute. And before I get started, I want to thank the judging committee for the Wagner Prize for the opportunity to present our work here. So first, a word about our collaborators. Tracy Gosselin's an associate vice president that has responsibility for the Cancer Center at Duke, and Amy Boswell manages the Chemotherapy Infusion Center within the Cancer Center. So they were very important contributors to the project that couldn't be here today. They're busy seeing patients, I'm sure. Chad is a healthcare administrator, and Michael Moore is an operations research analyst that contributed to some of this work, which was collaborative between Duke and North Carolina State University. So I'm going to tell you a little bit about Duke Cancer Institute. It's one of the largest and best cancer centers in the United States. They serve over 50,000 patients a year, and they have clinical and research partnerships all over the U.S. and all over the world. And one thing I'll make particular note of is that the total investment is approximately $400 million. So this is a very expensive resource that many, many people count on a daily basis for cancer treatment. And they face a lot of challenges. These are challenges that many cancer centers face. There's simultaneously increasing demand in the needs for cancer services. And there's also a shortage of oncology services, particularly nurses, experienced chemotherapy nurses. So this causes long patient waiting times, very high utilization of resources, congested environments that are difficult to work in and difficult to be in for patients and for nurses. And this is in part due to high variation and uncertainty in the day-to-day flow through the cancer center, the flow within the day in the cancer center, and the fact that the flow and the service times are largely unpredictable. So uncertainty is a big element of fixing some of these problems. So some of our goals were to try to improve broadly patient access. And that means improving how timely treatment is, throughput through the cancer center, and trying to reduce waiting time for patients. We are also aiming at trying to make the workload more distributed and manageable on a day-to-day basis for the nurses that are working in the cancer center. So these are our major goals. And I'll tell you just a little bit of background on the project. One of our non-operations research challenges that we dealt with was trying to overcome a very significant NCAA problem that we have with competition between Duke and North Carolina State University in terms of basketball and football. So we were able to work very successfully with this other wonderful organization. And it started with Jonathan Woodall, who was a graduate student at the time, doing a summer internship, working on all kinds of things related to the Cancer Center. And later that summer, Tracy Gosselin, the vice president with purview over this project, called me and asked if we could extend the project to a one-year project where we would look at trying to make improvements in the outpatient treatment center at Duke. And so they funded a research assistantship that ultimately funded Jonathan's time to do his master's. So this was really his master's project. And we had regular meetings. Jonathan was there several days a week. We'd have regular weekly meetings and also quarterly milestone meetings where we would talk about some of the most significant deliverables about the project. The project completed in July 2011. Jonathan was hired at Duke. That's one of the best outcomes of this project. And he's continuing his work there, applying a lot of the ideas that we developed from this project. So some of these things are getting infused throughout the Cancer Center and other parts of Duke Medicine. So a little bit of background. That's a quick introduction, and now a summary of our talk. I'm going to tell you about how cancer centers work, a short tutorial on cancer center operations. And then Jonathan's going to come up and tell you about the simulation model we developed for the Cancer Center and a nurse scheduling model for the Chemotherapy Infusion Center. And then I'm going to come back and tell you about some of the conclusions and some of the things that we implemented as part of this project. So here's a quick overview at a very high level of how cancer centers work. There are a number of important areas. Most patients arrive and go directly to the clinic. The clinic's where they have one-on-one consultations with their oncologist. Most patients have a blood draw and a specimen sent to a central labs area. And central labs evaluates that, and that's a critical part of the oncologist determining if the patient is progressing through their treatment and whether they can actually have treatment that day. So after the clinic, the patient moves to the OTC. That's an acronym that'll come up many times. That's the Outpatient Treatment Center. And the information from central labs has to flow over to the pharmacy so they can mix drugs that will come to the outpatient treatment center. Now, the patient can actually have the chemotherapy treatment once the drugs are available and other resources like a chemotherapy chair or bed and a nurse. So many things have to come together for treatment to initiate. And what they were seeing, because they're downstream in the overall process for the cancer center, is very long waiting times, which is bad for patients, and it was also decreasing morale for nurses working in the treatment center. So I'm going to dig in just a little bit into the clinic and the outpatient treatment center. So the clinic is where the patient sees their oncologist, and they arrive typically on time. Punctuality is very good here. They go to a waiting room. They wait for a blood draw. And then if an exam room is available, they'll go directly there. They'll have their vitals checked. They'll have consultation with a nurse. And they'll wait for their oncologist consultation. On the other hand, if a room's not available, they'll go to a separate vitals area once that becomes available, have their vitals taken, and then they'll go back to the waiting room. They wait there until an exam room and a nurse is available to start the consultation, and then they wait for their oncologist to arrive. Okay? After meeting with the oncologist, they check out. Some patients leave the clinic, but most proceed on to the treatment center. So this is the upstream part of the process. So let's take a look at the treatment center. I'm going to break it into two parts. The first is pre-treatment. Okay, and there's two flows that are going on here. One is the patient flow, and one is the information flow that happens in what's referred to as the back of the house. Okay, so the patient may be largely unaware that this information flow is going on. So from the patient's perspective, which is at the top right here, the patient checks in. They have their chart pulled and brought to a charge nurse. They go to a waiting room, and they wait for a nurse to take them back to the treatment area. From the information flow part, the charge nurse enters information into the computer system, checks the chart. If the order's complete and the labs are okay, then the pharmacy starts mixing drug, and the patient waits until the drugs, nurse, and other resources like a chemotherapy chair or bed are available. On the other hand, if the order's not complete, or the labs aren't okay for treatment, then they have to contact the oncologist. And that has a delay associated with it. It's highly variable what that delay is, and this is one of the challenges that they have to deal with. So if we zoom in a little bit more on the actual treatment center process, treatment is very complex, but from a patient flow perspective, it's quite simple. Treatment's either in the form of an injection or an infusion. Injections are easier. The nurse administers the injection and the patient is discharged. If it's an infusion, then they have to have an IV hookup. Infusion times vary significantly. So infusion can involve one or up to half a dozen drugs being infused. And the times vary from 1 to 6 hours. And they're highly uncertain depending on whether it's a new patient or an existing patient and how they react to the drug treatment. After infusion, the nurse unhooks the IV and then the patient's discharged. So that's just a short tutorial on how cancer center operations work. And now Jonathan's going to tell you about some of the models that we developed to help solve some of the challenges related to the outpatient treatment center.
Thank you, Brian. As he has already mentioned me, I am Jonathan Woodall. I work at Duke Cancer Institute. And now that Brian's given us a real good background about how the Cancer Center works, I want to talk just a little bit about the models that we developed to work on this project. And so just as kind of an intro, there were several models that were involved, so hopefully I can get them all straight right now, and I'll try to refer back back to them as we continue this talk. But the initial model that was developed during the summer internship was more of a hospital-wide simulation model. It included the incorporation of all the different cancer clinics, labs, radiology, the treatment center, all of those different pieces interacting together, and really serve the purpose of helping us identify what are the bottlenecks being faced by the cancer center. Near the end of the summer, we identified what bottlenecks were in the clinic as well as in the treatment center, and leadership made the decision to focus on the treatment center, largely due to the fact of the unpredictability of what a day would look like because of it being so far downstream in the process. And so at that point, for computational reasons, primarily, we honed in on just the treatment center and isolated that into a simulation model of its own. From that simulation model is where we developed a simulation optimization to look at nurse scheduling, which was primarily focused on a daily schedule. When should a nurse arrive during the day? And the third model that we'll discuss is a mixed integer program model, in which we looked at more of a weekly and monthly scheduling of nurses. So there's going to be all these different pieces, and I'll try to mention which model I'm talking about before I move forward. So with regard to the hospital-wide simulation model, I really just wanted to illustrate the process that was involved in building the model. There was a lot of different people involved in the construction of the model, a lot of different steps and processes involved. Wherever possible, we wanted to use historical data that was available. In some cases, that was not possible, and we spent a lot of time working with staff, what we call expert opinion, be it nurses, administrators, physicians, to get a sense of what is seen on a day, what is the variety of things that are seen, from what is most typical to what is maybe the shortest or the longest times that may be seen. And we also were able to conduct time studies for 2 or 3 different processes in this project. Specifically, for all of our patient arrivals, we were able to use historical data. There is a tracking system database at Duke that has timestamps from whenever patients checked in. And what we found is that these arrivals by patients were varied significantly by time of day. So we developed a non-stationary Poisson arrival process for our model. And for our service times where we had data, we used ARENA's input analyzer to fit probability distributions. And in the other cases where we had to solicit expert opinion, the majority of the distributions were fit using a beta distribution, where we took inputs on minimum, most likely, and maximum process times and kind of shaped a distribution to put into the model. In terms of validation, there were 2 main criteria we used for validation. How many patients get through the clinic? Does it match what we see in our historical data? And how long does it take a patient to get through the cancer center? Does that match what we expect? And then we also had a lot of talk back and forth with the experts in the cancer center to try to validate that our model was working appropriately. So the table that you see on this slide shows our arrivals in the simulation model. I believe this is Wednesday's data versus the historical data, and all of the confidence intervals overlap. We concluded that we were appropriately modeling our patient arrivals. In terms of validating flow time, we had more challenges because of the way the database tracking system works at Duke. It's not used 100% of the time for all the different timestamps, and there's something involved with checkout that they call express checkout, where a patient will drop their encounter form in a bin and will leave, and it might be hours later before the receptionist enters in that that patient is checked out. So the data we had available for validating flow time was limited, so we had to rely more heavily on expert opinion around turnaround times for patients. So to discuss some of the results of our initial model, we identified two primary bottlenecks in the clinic, one being phlebotomy, one being the oncologist, and then in the treatment center, chairs and nurses were the primary bottlenecks. The graph that's shown on this page really serves to highlight when in the day waiting time typically happens. This graph is real time from one of our simulation runs, very typical of what we see in the cancer center. And there's this ramp up in the day where there's not a whole lot of waiting going on, and then boom, right in the middle of the day, there's a whole bunch of waiting, and then you have a ramp down at the end of the day. And so this posed a significant challenge to the leadership in terms of how do we staff our nurses then, because our nurses are staffed on 8 and 10-hour shifts across the day, but we're seeing peak times in the middle of the day. How do you deal with that? And so that was some of the logic and reasoning that led us to look into just the treatment center. Some other background that's probably helpful is Duke recently opened, and at the time was in the process of building a new cancer center that would alleviate the bottleneck of chairs. So the question posed to us was, how can we, in the interim, reduce the bottleneck for nurses, and are there any principles that can be carried forward when we move into the new cancer center? So just a little bit more background on the oncology treatment center. This is where chemotherapy is received. We're not talking about radiation oncology. It's just a chemotherapy center. They tend to be split into disease-based groups where they take patients with similar types of cancer, and there will be nursing staff dedicated to just that group of patients. And I think I've listed all the clinics here on the slide. There are numerous clinics, again, feeding into the chemotherapy center. This graph shows patient and arrival data for fall of 2010 when we were working on this project. And there are two important things that I want to highlight in this graph. First, I've added a linear trend line to show the increase in demand. That is increase that has continued at Duke and is expected to continue in the future. And the other thing that I wanted to point out is how it jumps up and down from day to day. So there's just a tremendous amount of variation to deal with, which creates a significant challenge for planning. This graph shows for the same time period when in the day patients are arriving. So the average number of patient arrivals for each hour of the day. And this explains why we see all of the waiting time in the center portion of the day is there's this huge amount of arrivals in the morning, and between the hours of 9 and 1 or 2 you probably see 70 to 80% of your patients arriving into the treatment center all at that time. And a lot of this is dependent upon the schedule of clinics with the oncologists, and is something that's very difficult to coordinate and control. So again, the question we were asked is, how can we cope with the situation that we see? So what we did is we developed models to look at nurse scheduling. We wanted to be able to optimize a daily schedule, but also weekly and monthly schedules within the treatment center. Our goals were to reduce patient waiting time as much as possible, as well as to maintain some of the scheduling requirements around off days and shift lengths that the nurses currently saw. We didn't want to sacrifice work culture in the process of reducing patient waiting time. So really what we're looking at is what combination of shift lengths on a daily and monthly schedule should be used and when should the nurses arrive. And really this is a very hierarchical approach to scheduling. The daily schedule, patient schedule, is really what dictates a weekly and monthly nurse schedule. However, when administrators schedule nurses, they generally start on the monthly level and work their way down to the weekly and daily level. So there's just a lot of interaction that goes on between the different pieces. And for our monthly and weekly scheduling, this is where we used our mixed integer program. So we're switching models here to the mixed integer program, and the mixed integer program sought to minimize total shortage hours. And what shortage hours are is, first, if we back up and understand that there's an expected number of patients on a given day, and associated with that is an ideal amount of nursing hours to process those patients. However, nurse schedules are fixed and limited in terms of the number of nurses that can be hired, and as a consequence, you can't always meet the demand that you have in the treatment center. And the difference between the scheduled nursing hours and the required nursing hours is what we call shortage hours, and that's what we're trying to minimize in this model. So we have constraints set up for each nurse to work a certain number of days and hours in a week. For a 10-hour shift nurse, they're going to work 4 days out of the week, and so we had to coordinate having an off day in the week. One of the things that was very important for them to maintain is that each nurse would have a 4-day weekend in the month, which would be an off day on Friday one week followed by Monday the next week. And so that was a little bit tricky to figure out. And then for quality of care reasons, there has to be 3 nurses in each disease-based group, as well as a minimum level of nurses in the treatment center. 13 is the minimum level at Duke, and that's only on Friday, the lowest volume day. In terms of decision variables, we were changing what the shift length was and when nurses were having off days. So the formulation, we kept track of everything primarily with binary variables, where if a nurse was working, it would evaluate to 1, and if a nurse was off, it would evaluate to 0. We have variables set up. Our variable X is for keeping track of a nurse working on a particular day. We have a variable Y that tracks when a nurse has a long weekend. And then a variable Z tracks the larger subset of if a particular shift type for a nurse has been selected, and is really used for internal tracking to meet our constraints. And then our shortage hours. And some of our parameters for each day of the week, we had required nursing hours, minimum number of nurses, number of days worked per week, as well as hours per day. We did incorporate fractions of FTEs, where FTE is a full-time equivalent, and this being to account for part-time nurses. And this is our actual formulation, part of it anyway, some of the more important constraints. Just a sample that we minimize shortage time subject to the aforementioned constraints. So now I'm going to move to the simulation optimization model for the oncology treatment center. The goal of that model was to minimize patient waiting time. Now we're looking at a specific day that we are able to simulate in terms of patients moving through the cancer center, how long they're having to wait. And we took some of the schedules from the mixed integer program, and then we used those in the simulation optimization model to then try to figure out what time of the day should the nurses be arriving. So again, very similar constraints, minimum staffing levels. There has to be 2 openers and 2 closers. And then when we developed our schedule, we manually had to set the off days into the model and then adjust the arrival time from there. And so we really went through an iterative process where we took multiple best schedules and used them in the simulation optimization model to see what happened. Our decision variables were indirectly the shift length, where we were changing the combinations of 10 and 8-hour shifts in the schedules we entered, and then the arrival time, the simulation optimization model adjusted. This is our formulation that we just described. Our variable A was just if a nurse was working, again a binary variable, and then we had constraints around opening and closing shifts. So those are the different models that we formulated, and Brian is going to take back over, and he's going to talk about the results of our model and some of the recommendations that we made from it.
Great. Thanks, Jonathan. So I'm going to show you an example from each of the two different models, one based on the monthly mixed integer program, and the other based on the simulation optimization model. The mixed integer program we solved on a notebook using Premium Solver with Excel. So branch and bound computation time was an hour, so we tried to find the best solution we could within an hour. The simulation optimization model was more computationally challenging. We solved that on a faster PC. We used OpQuest with Arena to implement this, and computation times were in the neighborhood of 2 to 4 hours. So the first example is based on the mixed integer programming model for the monthly schedule. And we ran many, many different scenarios. This was a very iterative process. So this is one example where I'm showing you 3 types of problems. One where there were 16 nurses on the bottom, 18 nurses, which was their baseline, and then a 21 nurse example, which is where they wanted to get to. And we varied the constraint on the number of full-time nurses. This was very controversial, the idea of using part-time nurses within the cancer center. So if we look at these 3 examples, for example, for 21 nurses, we've got a constraint where there's no constraint on the number of part-time nurses. We have to have at least 12 full-time, and those could be 10 or 8-hour full-time nurses, and then they all have to be full-time. In terms of the objective, what we see is a fairly significant change in the number of shortage hours. And this just sort of illustrates what we saw repeatedly for a number of experiments, which was that basically a small number of part-time nurses could have a fairly significant impact on their total shortage. That led to some recommendations that I'll talk about in a moment. One more example from the simulation optimization model. Here I'm showing you instances for Monday, Tuesday, Wednesday through Friday, because those are very different days. The type of patients, the number of patients vary significantly from day to day, largely driven by the oncology clinic schedules. And so I'll focus in on one of these here. We'll look at Friday, and I'm showing you 2 columns. One's what we're calling the original schedule, and one the optimal schedule, and that should be optimal in quotation marks because we're really using a heuristic here. The original schedule was developed with a lot of input and collaboration between Jonathan and I and the folks working in the cancer center to try to improve the schedule by using data analysis and in a more ad hoc way. And then we used the simulation optimization model to see if we could improve on that. So if we look at the Friday case, for example, we saw statistically significant differences in a couple of cases here. For example, 36.77 minutes down to 28 minutes. That doesn't seem particularly startling. You know, lower is better, of course. But if you actually look at the distribution, there's a very big impact on those patients that are most affected. The 5 or 10% of patients that actually wait 2 hours, their times were coming down significantly, more to the 1 hour territory. So this looking at the average hides the benefit from those most affected patients somewhat. So I'll just briefly talk about some of the findings from the project. In terms of general findings, using the overall simulation model, we identified a number of bottlenecks. Some of these they knew. They knew the outpatient treatment center was a bottleneck. They knew the oncologists were, and probably should be, because oncologists are a very expensive resource. It was a surprise that phlebotomy was a bottleneck in the process. So that was an interesting finding. We found that there's very wide variation in patient waiting times. Many patients have 0 waiting time because they arrive to find the treatment center empty at the beginning of the day. But those arriving later in the day have very high waiting times. We found a trade-off in the benefits of adding part-time nurses, and we helped them to understand the potential benefits of adding part-time nurses to their schedule. And we also found changes to arrival and departure times for nurses could substantially impact patient waiting times. So in terms of things that were implemented, this is a summary of some of the most significant things that were implemented. They decided to change their policy and start using some part-time nurses. So they were hired to assist in better meeting day-to-day and within-day peak demands. The start times for the nurses during the day were moved around. So they were staggered. Some were moved up and some were moved back to the half-hour mark. And that had a pretty significant impact on the total waiting time. One of the areas in the outpatient treatment center, we found that it was a bottleneck. And so they added additional nurses to that area. And then we helped them to understand that 12-hour shifts were really hurting their ability to, on a long-term basis, match supply and demand. And so they're moving to 10-hour shifts. I think it's worth noting that of these four, the first three were very popular among the nurses. The fourth was popular except for those people that had the 12-hour shifts. So, but they were able to make that change. We also made a large number of recommendations on physical and staff resources that were required as part of a planning process for a new cancer center that they were developing. So we created these models for an existing cancer center, but at the same time, they were building a new cancer center. And so we helped them with a lot of what-if questions about what resources they needed. And those were a number of those recommendations were put into practice, and it helped them. That cancer center went live in spring of 2012. So I'll just make one or two final comments here. There are a lot of things that don't show through from the project. I would say they are not directly related to maybe operations research models, but over the course of this one-year project, and with Jonathan especially working closely with these managers in the cancer center, there was really an infusion of understanding of ways to improve how they're managing their cancer center. And although it's hard to distinctly point to any one of those, there was really some help for them in changing their culture. Now Jonathan's working over there as a full-time employee, and that's sort of continuing, so that's very nice to see. We also helped them a lot, I didn't mention much about this, but with their long-term resource and capacity planning. So for the new cancer center, we helped them understand what a 5 or 10 or 20% increase in patient demand, which they're projecting, would mean, and how they'd have to respond to that down the road. So with that, that's the end of our presentation, and we would be happy to take questions or comments.